for clients over time. So just a bit of a history of why I did this research. Part of my job at CCG is I'm a support scientist. So when we have clients, we'll sign CDAs and NDAs with them, and they'll actually send us the systems and tell us what they're working on. And we'll help them model a little bit, sort of like teach how to fish so you can fish on your own. So this started with a client who wanted to start a virtual psychedelics company and have sort of virtual learning, as an offering. Of course, that didn't work out. So that's why I can show the research, because the person actually couldn't work for us, so it actually worked out pretty well. So this is, probing the psychedelic structure activity space using pharmacophores. So psychedelics are fun, but pharmacophores are also fun. So I get to talk about both of them together. So it's going to be fun. So here's an outline. I'll talk about classical psychedelic drugs, the history, and the renewed scientific interest, which in itself could fit an hour talk easily. The pharmacophore is a device that summarizes SAR data, which is something I think people don't fully appreciate. And that's what I really hope for you to take away technical from this talk, right? The pharmacophore is the system I'm talking about, but it's a computational chemistry talk. And I think pharmacophores have something to offer that we know about them, but maybe we don't fully exploit them. And I'm hoping this is a system that shows you why we can do that. And as tactically, I'll probe the SAR of Schoen's classical psychedelic data sets, the FeCal and TCal books. Those of you who know them, will put your things up. Those of you who don't, it's a very interesting story that I'll get to. I'll create pharmacophore models from those classic compounds using the place known psychedelics, and then use them as in the context of virtual screening to go find new psychedelic molecules. I'll go into more depth there. I'll apply it to and compare it to docking, and we'll discuss a large-scale docking result and compare and contrast pharmacophore searching with docking. There's two ways of approaching virtual screening from a 3D perspective, and everyone kind of knows about docking, but pharmacophores maybe not so much. And then a summary conclusion, and there's a few other little confounding scientific issues about this that I'll bring up. And that's what I found fascinating about the system. Okay, so the classic psychedelic drugs, LSD, psilocybin, mescaline, and DMT, are called serotonergic psychedelics because they all act on the serotonin system. So serotonin, also called 5-hydroxytryptamine, 5-HT, is the structures up there. You see psilocin, so psilocybin is just psilocin with an extra phosphate group, which gets metabolized. Psilocin is the active molecule, and you see it looks very much like serotonin. One of the main differences is the dialkylation on the amine. Mescaline is another psychedelic that comes from a cactus, and that's actually an amphetamine type. So this is what's called a tryptamine type of psychedelic. DMT, dimethyltryptamine, that's another tryptamine-based psychedelic. LSD, as you can see, has a serotonin core. So it's called an ergotamine, but in a sense, it's a rigidified tryptamine, right? What's cool about this is that if you're 5-H, so these things act as 5-HT receptor agonists. But if you give someone a 5-HT receptor antagonist, it stops them tripping. So if someone's like really tripping on LSD, you can give them risperidone and it'll bring them down because it goes and it antagonizes the receptor instead of agonizes it, displaces LD and stops the effect. The natural products have been around for centuries. LSD was first synthesized on November 16th, today, but in 1938. So today's the 85th anniversary. I did not plan it this way. One of our, is it Andy? Andy Maynard told us about this. So one of our clients said, hey, did you do this on purpose? No, we didn't. So these were prescribed actually psychotropics in the 60s. There were tens of thousands of papers written on how these things were good for depression, etc. But because of bad press in the 60s, they were classified as Schedule 1. Research stopped, people forgot about them. But there have been researches recently. There's lots of things that are very promising about them. There's lots of studies on this. So our goal scientifically here was to develop a pharmacophore for psychedelic action. Why do we choose this data set? Well, it's interesting, but it also involves flexible receptors that adopt agonist-antagonist conformations. Ligand activity has profound activity cliffs. This one atom in the middle of nowhere totally changes everything. Why? I don't know. It's at the limit of some bottlings. Like not all 5-HT agonists are psychedelic. Docking scores and even binding energies, even experimental binding energies, it's hard to differentiate between what's psychedelic and what's not. So can we somehow learn about this despite these confounding things? So why is there renewed scientific interest? Potential to treat multiple disorders. Depression, PTSD, near-death anxiety. The treatment typically takes only a few sessions. They go into an office, they put blindfolds on, they take a big dose, they're with the therapist, they talk it through. They can be cured of things like alcoholism in 2-3 sessions, unlike most antidepressants, which take months of switching the drugs and mixing them up. There are some beneficial non-psychedelic effects. The studies have shown these have neurogenicity and neuroplasticity. So there's a lot of promising things about them. And culturally, many people are starting to self-medicate. You might have heard in some movies, people are microdosing. What's microdosing? They're taking sub-perceptual amounts of LSD or magic mushrooms. They don't get high, but they're using it to treat their own anxiety and their own depression. There's no definitive proof that this works, right? But it's used to enhance creativity, replace standard depression medication, but no definitive proofs there. What are the pros of this? It's not habit forming. Unlike a lot of drugs, it's almost impossible to get addicted to psychedelics for a couple of reasons. There's a quick refractory period. You take LSD for 5 days in a row, after that, it'll do nothing to you. You actually gain resistance to it. And there's cross resistance. You take LSD for 5 days, you're resistant to mescaline, you're resistant to psilocybin, but not DMT. Talk about that later. Natural products are cheap, right? Magic mushrooms on the black market, like $4 for a dose. So it's, I looked on the internet. They're illegal in some places. Right? It's legal in Massachusetts now. I never thought this would ever happen, right? So, but also profoundly non-toxic. So here's LD50 over ED50. So lethal dose versus the effective dose. So this is how much do you have to take to kill you versus how much you have to take to get high. So that's why heroin and alcohol are very dangerous. The amount to kill you is only 6 times the amount to take to get high. So get some extra pure heroin you're not used to, double the dose because it's Friday. You can easily make it better up to 6. Alcohol, 1 to 10. You take 3 beers, 30 beers will kill you. Caffeine, Prozac, aspirin, LSD, psilocybin, greater than 1,000. Cannabis, of course, greater than 10,000. No known overdoses from cannabis or LSD. That's chemical overdoses. Maybe on LSD they drove the truck off the cliff. That's different. That's not a toxic overdose, but there's not many records of that either. The con is the trip necessary? Can I cure people with depression and all these different things without having them to go through that trip? Because it can be unpleasant. That's probably why some reasons they're not addictive. It doesn't always make you happy. It can make you messed up, right? And as far as pharmaceuticals, we can't patent the known drugs. They're cheap to make. They've been around forever. So can we dust off new ones? Can we develop new formulations? Can we develop new compounds? So in the process of doing this research, I learned so much about systems I didn't know about. For those of you who know me, this is not yet another kinase. I've seen so many kinases, but now working this receptor system is interesting. So psychedelics interact with the neurotransmitter system. So nerves communicate along the axion electrically, but when they get to the other nerve, they communicate with neurotransmitters, and that transmits the signal. So the neurotransmitters we're going to discuss here that are implicated in mood and psychotropic drugs are serotonin, dopamine, norepinephrine. And this is a better, more detailed view of the system. So your body synthesizes the neurotransmitter, which is the little red square. It gets packaged in these little things called vesicles with a protein called VMAT. When the signal comes, the vesicles release the neurotransmitter in the cleft. It hits the GPCR. That's the receptor. So the receptor is either for serotonin, 5-HT, for dopamine, D, 1 to 5, norepinephrine, the alpha and beta ones. 5-HT3 is actually an ion channel, so it's not counted there. Then the signal happens, then the neurotransmitter gets recycled. It goes to this thing called the transporters, put back in the cell. So the transporters are SERT for serotonin, DAT for dopamine, NET for epinephrine. And when it's in here, there's a chance of being broken down by MAO, which degrades it, and then it gets recycled. So that's that's the cycle of how the neurotransmitters work. So if you look at psychotropic drugs, so this came clear to me how all these different medications work, right? If you everyone's heard about SSRIs, selective serotonin reuptake inhibitors, selective norepinephrine reuptake inhibitors, these things target this. They keep the basic theory as I understand it is when you're depressed and anxious, there's not enough neurotransmitter here. If you're psychotic, there's too much neurotransmitter. So you're trying to turn the dial for the neurotransmitter level in the cleft. So depression, anxiety, low level neurotransmitter, we have these reuptake inhibitors to try and stop that reuptake. There's another type of antidepressant, MAO inhibitors. They try and stop the degradation of the neurotransmitter to keep it in the system. Cocaine is actually a non-selective SERT-DAT-NET inhibitor. So cocaine works because your cleft is always flooded with neurotransmitters, so it's making you feel good, right? MAO inhibitors are interesting. They're taken off the market a lot because they're dangerous. You can eat some sort of cheese, and all of a sudden that cheese is toxic because you're not this thing to break down the amine. But if you ever heard of the ayahuasca mixture, this is a Brazil thing. They go and they mix this brew and they drink it. It's got a combination of DMT, which is not orally active, but the brew itself has a MAO inhibitor. So you combine the two, the MAO inhibitor and DMT, and then it's DMT orally available. Ecstasy works on VMAT. It screws up VMAT, so instead of packaging into cells, the whole presynapse is flooded with neurotransmitter, which leaks in. So now you're really happy because you got a little of this leaking neurotransmitter into the system. Antipsychotics, they antagonize the GPCR. And as I mentioned before, they'll actually stop the signaling from psychedelics. Psychedelics that either agonize or partially agonize the 5-HT2A or 2B receptors, sometimes 2C, and that's how their effect works. So this is a slide on why do they work? And this is kind of what the theory is, at least I understand it, is that when you overstimulate the serotonin receptors, they start to go back into the cell. What happens is the cells stop talking to each other. So this graphic here, which I don't fully understand, but what it's trying to show is in the normal placebo brain, not on mushrooms, your brain's got certain default mental network pathways, the things you think all the same time, especially with depressed people and traumatized people, these constant thought pathways, they're always laminating on, right? And that's causing their problems. So when you get into psilocybin, it blocks those highways, and now they can find new ways to think about things chemically because they're forced to, because the neurotransmitters shut down those pathways. That's why it expands your brain, right? So that's the idea of why it works. Now let's go to the model. So now we'll look at some structures now and all this kind of stuff. So there's two main classes of psychedelics that are known and actually been studied over the years. One's based on serotonin, so the ones that are called tryptamines, and ones that are based on sort of the dopamine type element, which is called phenethylamines or amphetamines. Now look at these kind of activity cliffs that I noticed. So these three here are psychedelic: DMT, psilocybin, and bufotenin. This is the one when you lick the frogs. That's the one that you get when you lick the frogs. But you take psilocin and you take the methyl group off, no longer psychedelic. If you take the position over here, you start adding some atoms, you get these molecules called triptans, which are a class of headache medications that's been on the market for decades. A few atom change, and it's something that's been around for forever. Same with the dopamine, mescaline and DOI. These are psychedelic. I change the I to a fluorine, lose psychedelic activity. If I put a couple extra methyls there, I lose psychedelic activity. So why is this? But they can still be agonists. So here's the 3D challenge. So there's this compound LSD. So we know that's psychedelic. Here's this compound Lysergic. So I've got two PDB files here, 5-TVN, 6-DRX. So I'm showing the 3D interaction diagram. Kind of looks the same. I'm looking at the docking score from our software, more or less the same, which you'd expect. The atoms are in the same place. I've got a view of the 3D structure here. Orange is LSD, and green is Lysergic, and all the side chains are almost exactly the same position. There's very little change in these. There's no obvious, oh, I opened up that pocket and it became psychedelic. Very subtle changes. And if you look at what's called the receptorome, okay, so for those of you who don't know this, right, I only kind of really started understanding doing this. Is a receptor is different from an enzyme. The kinases, you go in the pocket, you hopefully stop turnover. With a receptor, it's got a basal response. Doesn't need a ligand. So the basal response is that green line. The full agonist serotonin will go to 100% response. Partial agonist, partial 100%. An agonist puts it back to basal response. Inverse agonist actually slows it down, and full agonist will stop altogether. So what this is showing, and both of these things are actually agonists. They're both agonists with about the same level of partial agonism. These are the different binding constants against what's called the receptorome. The serotonin receptors, dopamine receptors, and generic receptors, and we're looking at the binding energies between them. And you see Lysergic actually binds better to 5-HT2A and 2B than LSD does. Why is Lysergic not psychedelic? I don't have an explanation from a binding energy, from a structural point of view. So this is where it's a piece of information that I know, but I can't encode it in a scoring function, but I can probably encode it with, there's something weird going on there. And that's where the pharmacophoric comes in, right? And back onto this idea of the psychotropic receptorome. So these are all the receptors, and there's more receptors involved. It's just a subset that are involved in psychotropic drugs. So when and this is actually a nice publication, Ray TS in 2010. There's the source. So what this is, a big panel. So you got a new psychotropic drug, test against this panel, it's sort of like a kinase panel, but it shows you the activity. So it's the LSD active against 5-HT. But also dopamine, and a little bit against alpha and beta, and a little bit over here. THC, of course, is only active against, CB1 and CB2. Morphine against the opiate receptors, nothing else in this panel. And there's some other receptors here. So that's the panel. So the thing I need is to look at a thing like this and say, well, that's going to be, an HG agonist, that's going to be an opiate thing, that's going to be a cannabinoid type thing. So we can use that to quickly visually compare the profile across similar molecules. And this is where it gets confounding, right? I've got these molecules, LSD lizaride. They differ by a single double bond in the ring system. And this is the profile of experimental activities across the receptorome. So there's only a couple little bars that are different. Another example, DMT, psychedelic, 6-fluoro-DMT, not psychedelic, and similar profiles. And these are experimental energies. So even if we had the experimental docking scores that match this perfectly, we still have a hard time to tell what's psychedelic, what's not. Because there's other things, maybe not the docking scoring function, maybe there's electronic effects, there's other things that we're having a hard time modeling. And it gets this where I guess principal slides have been bothering me. So 5-HT2A is the main one that people think is responsible for psychedelic effect. Maybe 5-HT2C, but mescaline doesn't hit either of them. I'm gonna have to look into this more. It doesn't bind, it seems. So that's again what's going on there. Maybe we don't know, right? And then users become quickly resistant to these three after 5 days, but not DMT. And actually, I saw something recently and I think why DMT is so greasy. It can actually go through the membrane and hit the retracted receptor. So that's how complicated it is. There's all these different things going on. Okay, so it's complicated. I'm never going to understand it totally. So here's what the talk about pharmacophores is really. Okay, and the talk here is this: that incorporating the pharmacophore as a device to summarize SAR data. So what do we have as computational chemists? We have a bunch of structural data, and there's different issues, different resolutions, and whatnot. We have models we've made from other dynamics or molecular modeling, docking, etc. We also have tons of 2D compound data, activity data, responses, etc. And we want to make sense of all this with our brain and sort of put it into one compact summary. And one way we can do that is with pharmacophore is a convenient device for that. So you can generate a 3D binding Bose hypothesis, especially if you have analog series, they all kind of bind in the same way. And then you can communicate those observations to everyone else. So showing here kind of this idealized pharmacophore. There's where the ligand can go, the ligand can't go there, and these features over here. What's nice about the pharmacophore is it's a cartoon to convey your observations, but it's also a 3D query. You can use to search compounds and then place 3D molecules. So it's a cheap Docker where you guide the placement of the compounds, not with the receptor, based on your knowledge of the activity series and your current binding hypothesis. And the thing is, it's a ligand-centric approach. You can use a lot of receptor information, but you can design a pharmacophore even if you didn't have this receptor information. You just start with 3D ligands if you were that confident. A rigid 3D ligand, whereas docking, I prefer to as a receptor-based approach because you kind of need a receptor. Okay, why chemists like pharmacophores? Knowledge can be incorporated into them. I could say, I want a hydroxyl there, whereas that modified scoring function is say hydroxyl scores well there, a lot of terms to do. It's an easy to use tool for placing compounds. I can just take the pharmacophore, give it a database, and it'll place them where I want them to be. Whereas a doctor may put them in places I don't want them to go. The results are easy to interpret. There's no score. It hits or it doesn't. And when you do a virtual screen, let's say you get too many compounds, well, I can make the radii smaller. I can make the pharmacophore more restrictive to bring it down. If you don't get anything, I'll make the radii bigger, make it a little more sloppy, and you get the hit list that I want. And it's also technically less challenging for non-experts. Like this talk is aimed at medicinal chemists as much as it is comp chemists, because medicinal chemists, they have binding hypotheses and they don't want to run a big docking run, but they might want to just make a couple pharmacophores and use that as a little bit of a search. So I'm going to show you sort of how this all kind of happens. And for the med chemists, it's kind of like, this is the thing I wanted them to think about. Is that in JMedChem, you make these 2D SAR cartoons that summarize all your observations. My thought is that, well, you can do the exact same thing in 3D, but that 3D thing can now use to place 3D compounds as well as do a virtual screen. So it gives you a little bit of extra, information on top of that cartoon. Okay, so how do we do the manual creation? And the brain is used a lot here in this case. So what I did was I selected some structures that had initial pharmacophore hypothesis, placed some known actives to see if my pharmacophore made any sense, did some modeling to make the pharmacophore a little bit better. And the main thing to emphasize here is the cycle. I'm going to improve the pharmacophore as I do new searches, find new actives and inactives. The pharmacophore is not static in time. It's continuously updated. I might split them into two pharmacophores. It's a meme for our current understanding of binding. So here's how I did it. So I started with one structure, LSD bound to 5-HT2B. And so there's the 3D structure for the PDB. There's the 2D diagram. Here's the 2D diagram summarizing the important interactions. I've got a cationic donor here. Now, and that cation donor is going to come up a little bit later, but that's common to all the aminergic GPCRs. Most of the aminergic receptors, they're classified that way because they react with small amines in the body. So almost all the neurotransmitters have this positively charged cation group. And we have that in LSD and almost all the psychedelics that we're going to look at. There's a little aromatic feature here. There's a projected feature here. There's a nitrogen here, but I know it has to interact with ASP332. That's the crucial residue that's interacted in all the structures we know. It has an interaction with the ligands. There's some aromatic stuff over there. I put a sphere there. There's a little dotted line that represents the extent of the pocket, but I can also represent the extent of the pocket by the extent of the ligand. So make this a 3D pharmacophore. I make a aromatic feature with a couple of normals to keep the aromatic oriented, a little hydrophobic blob, a cation, which is also a donor. I make an excluded volume. So that's a region where the ligands can't go. That's where the aspartate is, because I know it's there. I'm ignoring the rest of the receptor, and then I'm making a ligand shape around the LSD. So that's my first simple pharmacophore. I can search with this. Now, here's where we start adding SAR information. So this picture shows LSD in orange in the 5-HT pocket, and the graphic that's drawn there is the van der Waals interaction diagram. So what that shows, anytime a heavy atom goes through that diagram, that means the ligand is crashing with the pocket. So I've got LSD bound to this structure, so the receptor kind of probably shrink wrapped around it. But then I look at my SAR data, and there's a whole bunch of class of compounds called ergotamines. They look exactly like LSD, but they got that big blob up there, and then they're non-psychedelic. So they're agonists, but as soon as you go up here, they start being non-psychedelic for whatever reason, right? There's a compound called LMD14. You can put a methyl group there. You lose a bit of psychedelic activity, but you're still psychedelic. The crystal structure says you can't go there, but I take the molecule, I still get high. No, maybe I can go there. There's this one thing of ALD LSD with a propyl extension off here, quite active, sometimes some purporting more active than LSD. That wouldn't work on our Doppler either. But when you extend to phenylethyl, then you lose activity. There's an interesting compound when you extend to bromine over here. You're still an agonist, but you lose psychedelic activity, and they still have neuroplasticity. So how do I incorporate all these things? What I can do is say, okay, there's my pharmacophore model. I'm going to model propyl off this and expand the ligand shape of LSD to incorporate a propyl. I know the protein can move there, or at least I think it can. I know bromo over there does something. So I'll put a little blob there. I'll make it what's called an excluded volume. Don't go there. If you go there, you must still be an agonist, but you lose psychedelic effect. So this is incorporating, some of the knowledge that I have to modify my shape understanding of the system. So I've got my first hypothesis. I'm going to test this on these two data sets synthesized by Alex and Ann Shulgin over 30 years. So they published books in the 90s called fecal, phenylalanines I've known and loved, TCAL, tryptamines I've known and loved. These are the two different classes, phenylethylamines or amphetamines and tryptamines. And LSD has the core of both of them. And what he did was he synthesized them. He was an organic chemist. He synthesized the compounds and tested them on himself. Small doses, increasing doses, and then reported the effects. So reported the dose, the duration, the subjective effects. And this is the data set I used. I didn't use activity data or binding data. It was like, is it active? Is it not active? That was my cutoff of things that are active or not active. So the first thing to do is to take my pharmacophore and search the TCAL book and search the PCAL book. Now you see the tryptamine core is very much like the LSD core. So the pharmacophore very easily placed almost all of the active tryptamines, no problem. The poses look good. The indole is kind of in the same place. Interestingly, it didn't place these tryptamine-like molecules that have the same sort of features, but they're locked in the wrong conformation. So that's actually kind of interesting. These things will bind, but they're not psychedelic. The phenylethylamines, pharmacophore didn't work so well. I only got a few hits, and the only hit I got was like amphetamine, the basic sort of skeleton. So I said, okay, that's going to be my starting point for modeling. Before I do that, so I've got the pose for the tryptamines. My question is, okay, this looks good. I'm happy with myself. Does it correlate with what Shulgin saw? So here's 5-methoxytryptamine. It's one of the most potent psychedelics. So it's just like dimethyltryptamine with this extra hydroxy. That's actually where the serotonin hydroxy would go. And if you look through his book, you look at the stars, like he's able to put some groups off the side here on the R groups up to a propyl group. And that's kind of like LSD. I can get a little bit of alpha extension over there. Once he started putting groups off there, he lost activity, just like LSD. So we've got that pose over here. The 6 and 7 positions, he lost activity when he put groups over here. The 5 positions that I mentioned before, they become tryptans, you know you lose activity here. However, if you cyclize the 5 and 4 position, you have some room. And indeed, if you do that, you get active compounds. So the pose is kind of matching the shape of the LSD, and it's matching the SAR. If you go there, you lose activity. You can go there. No, I didn't lose activity. So then, but the tryptamine, so I only had one tryptamine pose. So I said, now I'm just going to be modeling. I'm going to take the most active amphetamine, model it, and I got this pose, and I found some interesting things. I found a hydrogen bond at the 4 position here, which corroborates with a lot of compounds. When you put the bromine in the 4 position, you get activity. The 2-5 position is actually a very privileged sort of arrangement with these things. So that kind of corroborated, it all kind of fits. The R configuration is more active, and if you model it, the R configuration fits in the small pocket, the S configuration points out. What was interesting was that most of them are monoamines. So they bind with the S, but they can also swing down and bind with the serine and form this bifurcated bond. So is that real? Wasn't too sure. So I looked at other crystal structures, and there are other crystal structures of 5-HT where serotonin forms that same bifurcated bond. So I've got a little bit of experimental evidence for that. This is the interesting position, the 2 position. If I extend the methyl over here to an ethyl, I'll lose activity. But if I take that group away, I also lose activity. So this gives me this other feature, I need something here. So that's the thing that sort of pharmacophoric can do that other things can't. So what I show here is 2 different pharmacophores that are summarizing the data. So the general one is for primary, secondary, and tertiary amines. I take the ligand shape and I expand it to fill my new molecular compounds. Then I also add a second position for the amines. The amine can move into the other position where it interacts with the serine. I also put this atom Q position. Atom here needed for psychedelic activity. I can be more specific. I made a pharmacophore that specifies the bifurcated bond, has all the other features, and again, this optional halogen bond feature to go and capture that observation that I've had. Now, so then I take that pharmacophore, and let's go do the searches again. So I take the general pharmacophore. It works really well on the tryptamine compounds, still fails on the phenylethylamine compounds. The phenylethylamine specific pharmacophore does well, but it misses a lot of actives. So here's where you can have a hypothesis. Okay, I'm going to run the thing again. I'm going to take away the ligand shape. Then I hit almost all the actives. And I look at the actives that I missed, and the actives that I missed have an extension over here. So these compounds have extensions in a region that in the crystal structure is blocked. So by placing the compounds this way, I'm saying, I think the receptor moves over here. Doesn't move in the crystal structure, but if these compounds bind in this mode, we know they're active, there must be some motion there. So, and then you can add some other information. I mentioned about ergotamines. They have this, if you superpose structures with this ergotamine and LSD, they're right on top of each other for the most part. But I know this is an agonist, but not psychedelic. So I can make a volume for just the atoms that go outside the LSD and say it's a non-psychedelic agonist volume. Maybe it's not accurate, but I'm hypothesizing here. I do the same thing for antagonist. I took an agonist, the LSD structure, and I superposed it with this risperidone. That compound I told you was the antidote for LSD tripping. So we put the 2 structures on top of each other. Now you start seeing kind of the changes you hope to see to differentiate compounds. The agonist opens up a little pocket that the LSD never goes into. This looked good, so we got more structures superposed on top of each other. Turns out that agonists never go in this pocket. A lot of antagonists do. So I can take those blue atoms, just select them, make a little blob, and say, this is the antagonist excluded volume. If you start going in there, you become an antagonist. Now, you might want to use it as an excluded volume. I don't go there, but maybe you want to turn it on later because you want to find something that looks like LSD, but can also be an antagonist. You're sort of summarizing information. So this is the summary, right? This is the summary observations. There's the LSD envelope. The pocket could open up here. Over here you get agonist activity. I seem to always need an atom there. Compounds that occupy that thing seem to have agonist but non-psychedelic activity. And this thing is very much like the 2D structure that a med chemist would use. So they're kind of very similar to each other. So being able to think this way The difference is I can now use the 3D pharmacophore for pharmacophore searching, fragment placing, docking, and other kind of 3D placement opportunities. Okay, so another simple pharmacophore I made was I looked at a lot of the antagonists. So a lot of the antagonists have this long kind of sausage-like shape where they've got sort of a minimal distance. So I made a very simple pharmacophore, which is these are three superposed structures, very minimal pharmacophore, the minimum distance between the two, the same hydrophobic donor receptor feature, cation donor feature from the psychedelic pharmacophore, then a big ligand-shaped sausage around all of them. So I can use that as a filter. When I passed it on the Shogun data set, I only found a couple of compounds which are actually inactive. So I found some inactive compounds that were in the Shogun data set. So just to show you what you can do with this. So this pharmacophore, if you know what you're doing, you can say it doesn't take that long to necessarily construct. You got a SAR table, right? But once you got the pharmacophore, you can search a database. So I did this test. I searched 600,000 compounds. It took 8 processor hours, so 75,000 compounds per hour. I got a low hit rate. You don't want to hit everything. And one of the reservations about using pharmacophores is you're not going to find things you don't know. And it's true. I'm not going to find things that don't have the features that are specified. But it doesn't mean I won't get diverse chemical matter. So I divided my hits into 2 types of hits, ones that are similar to the Shogun sets. And that's the point. If a med chemist can look at this, I read Shogun's book. I could have guessed that compound. I'm not making too much addition. These look a lot like the tryptamines with some extra stuff. But these ones start looking a little bit different, things that have been hard to imagine. So these are with max similarity lower than 6.5, higher than 0.65, and there's a distribution of the max similarity. So this shows that I can find compounds dissimilar to the training set. So at this point, I wanted to, again, contrast this with docking and pharmacophores, because they're actually, they're complementary, but they're different, right? And they don't have to be at odds with each other, but the philosophy is going to, with docking, you've got a physics-based method, you've got energy functionals, you've got a scoring function, you need a receptor. In principle, you can find compounds that exhibit specific bonding modes you've never seen before. That's the goal. Okay, we've got a crystal structure, there's a ligand down there. I do docking, I find some ligand up there. It's got a good docking score. I synthesize it, great energy. It's actually active. Real cool discovery. It is dependent on the 3D structure, which limits the representation. Even if you have a flexible docker, it's not going to make the protein do these crazy things. You can make the protein do crazy things and then dock to it, but it's limited by that. The pose is what you get. It's hard to say, I want the docker to give me a pose that has this, this, and this. Some dockers have that ability, some don't. It asks the question, can I place the ligand in the pocket with a good score? And it's typically slower than pharmacophore searching. Pharmacophore is opposite, not physics-based, kind of knowledge-based. Will not find compounds with a completely novel set of features by definition, but you don't need a 3D structure necessarily. You can represent protein flexibility quite flexibly with these volumes. And there's a precise ability to say, I want molecules fitting that pose, which is the kind of thing that a chemist might ask. And it's typically a lot faster. So I compared this to a study. So I started doing this research maybe in like 2018, sort of on the side, And this paper came out in 2022. It's quite a monumental effort in some ways. So there's a big, huge paper looking for new 5-HT2 agonists. And the way they did it was they built a whole bunch of homology models, and they built thousands. From that, they chose one. So the first thing that came to my mind is that's kind of limiting the flexibility. So they docked 75 million virtual compounds quite quickly, but again, 10 times slower in the pharmacophore search, and this is on a bunch of cores. But then they got 75 million compounds with scores. So what are you going to do? They clustered the top scoring 300,000. Then they kept the top scoring 4,000 clusters. Then and look for this when looking at docker, this pose inspection. And I kind of quote here, inspect the pose for features not accounted for by the docking scoring function using unsatisfied hydrogen bonds interactions. That's a pharmacophore. They could have used that up here. Maybe that would have get the clustering. So after that, they selected 2 compounds based on dissimilarities in actives. They want to find novel stuff, right? 17 selected for synthesis and testing. So I looked at the results and I divided the results into the left and the right. The left was, I'm not so impressed because this looks very much like the tryptamines that in Shogun made compounds that looked almost exactly like this. These are very similar to known compounds. They are agonists. These ones all hit by psychedelic pharmacophore. This one also hit the antagonist pharmacophore. And it turns out when they tested it, it's actually an antagonist, but it's probably luck. This is a pretty crude model. Now, these other ones were actually impressive. These look quite different, right? They look different than the tryptamines. I can't really see the core necessarily. The red indicates that they hit my psychedelic pharmacophore without the atom Q feature. That's nice about pharmacophores. It doesn't hit. take away a feature, take away another feature, rerun it. Oh, that hits as long as I take that feature out, which can tell you something. Maybe your pharmacophore doesn't need that feature. Or in the case of this case, so I use the pharmacophore to place the known compounds, and the known compounds are they actually crystallize one of them. 7 rand is the structure. So my place compounds are in green, the known compound is in ball and stick. But by now, we've got the canonical indole pose, it's kind of always there. Now the other ones, now that I placed with the pharmacophore, the pose became a little more clear to me. It kind of, this replaces the indole system. There's the same cyclic amine and some stuff extending here, but the atom Q is not satisfied. So it gives you also a suggestion of what you might want to add there. Maybe, I can take that molecule and make it better by putting an extra methyl group there. So, and this final slide shows for maybe the unconvinced that, in both cases, pharmacophores or docking, you can get a diverse set of stuff to go increase your imagination. And the story gets a little bit, I still got some time. Excellent. So these are the additional slides, some of the additional slides. So the story gets even more exciting in the sense that I did all this work, and then this crystal structure 7WC5 comes out. And psilocin is not in the canonical flows. It's way up here in the pocket, right? And they got one with serotonin. So I'm thinking, okay, I'm taking all the slides before this, and I'm going to press delete. But if you look at the pose a little more closely, so there's a couple things. If you look at all the 5 HT structures, what I'm showing here is all the indole rings that aren't extended, from the 5 HT structures. There's a canonical indole position at the bottom of the string where things kind of move around, which gets disrupted if you start adding big bulk in different places. But for the most part, it's indole's clean around there, it'll be there. Whereas the cyan structure is from the 7 WC5 structure. Then you look more closely in the 7 WC5 structure, and this surfactant molecule in the crystal structure that's occupying the pocket where psilocybin has to be. So maybe that, psilocybin's got to get in there, right? So maybe they've just crystallized in an intermediate state where it's coming down. What's interesting about this pose too is that it opens up a big pocket where the surfactant molecule goes, and that's not open in any other 5HT structure. So it gives you another place where the protein can move. So this is a way of using your pharmacophore or your SAR data to look at a new, like this could have been a docking pose or a crystal structure, say, do I trust this? So I want to move forward with this. So that was one thing you can do. And here's a bit of flexibility stuff that I did too. So you extend phenylethyl, this to the phenyl group and LSD, lose activity. But if you extend, to a phenyl group on amphetamines, you can get these very active compounds. The bromo N-bomb is the example here. So I tested these with my pharmacophores. With that extension, no hit with ligand shape. This one was able to hit with ligand shape. It kind of curled around a little bit. But as soon as I take the ligand shape away, it shows me where these conformations would clash with the normal shape, right? So the LSD kind of sticks out here, and the N-bomb kind of sticks that way, but a little bit different. So when I look a little more closely, so LSD kind of sticks over here, but you see with the N-bomb conformations, it has more of an ability to actually superpose on the tryptophan ring. So I knew about this beforehand, so I didn't discover this independently, but there's a huge protein motion where it turns out that, so if you didn't know about this, and you're doing pharmacophore, you say, look, I know this compound's active, there's 2 possible poses. It either bends around like that, or it goes and it occupies a place where LSDs can't go, so well, maybe it can occupy there as active. So you can say, I'm going to put a tentative volume here. Maybe phenylethylamines can put something there and still be active. And it turns out in the crystal structure, it actually does take away from the tryptophan, which moves, and the structure kind of bends a little bit, a big pocket opens up. And it's the only crystal structure we see that. It's the only ligand that makes that residue move out of place and open up a pocket. Just like the other one, that's the only crystal structure where that region is open in the GPCR. Now I've been starting with the ligand as the center, but you can also use pharmacophores to exclude a volume. What I start as the protein as the center. Instead of having a protein pocket, let's make volumes for all the backbones and volumes for the different residues, and say, look, I'm going to make a run where that residue is not there anymore. I mean, you could do the same thing with docking too, just by deleting the residue in some ways. But it gives you an idea of how to explore protein flexibility. And the final, I got some minutes for this, which is good. Okay, so I searched all kinds of crazy stuff on the internet, looking for this stuff. And there's this web page called Psychedelic Wiki, where it's a website for people who use experimental psychedelics, experimental. They're called psychedelics. People who, try and be smart about the drugs they take. And it lists a collection of non-classical they've divided them up into serotonergic. They've actually done a pretty good job of doing this. And unlike a lot of the other papers I saw, they found some things that were very interesting. So there are some known molecules here that are known to be psychedelic. Why? Because people are abusing them. And so these ones are all protonated amines. So they look very much like the things you've been studying. Hopefully to this point, you can start seeing, oh, there it is. Oh, there it is. Oh, there it is. Oh, there it is. You know, they'll become like a med chemist. But then there's this one, which doesn't have a positive. So efavirenz is it's an HIV medication that's being abused apparently in South Africa as a psychedelic. So I used my pharmacophore, I adjusted the ligand shape a little bit, and I was able to place all of these, and it kind of corroborates kind of what we see. Okay, so the amine, the little ethyl thing, some aromatic thing, and some atom occupying over there. They can all sort of match that pose. But of course, efavirenz can't. And this is an example where pharmacophores would completely fail because this doesn't match that crucial feature that I think is crucial for bonding to aminergic amines. So it's very interesting because it seems to have serotonergic action. I haven't read the papers, I've read papers that refer to the papers, but the experiment showed it actually displaces LSD. Because maybe it's got psychedelic action, maybe it's allosteric, right? It has no basic center, unlike the vast majority of psychotropic drugs, except cannabis, right? There's some that don't, but they're called aminergic receptor GPCRs specifically because of that protonated amine. And since it lacks the basic center, it's not placed with the pharmacophore. So this is where, if I was someone working in this field and I had access to crystallography and all that kind of stuff, I wouldn't have crystallized the thing that looks exactly like Shogun's compound. I would have crystallized that thing if it's possible, right? Because this is going to be something, this is complete knowledge, right? This is something really crazy and new. Whereas I'm crystallizing something, I mean, you should crystallize, I'm not dissing them, don't get me wrong, but I'm looking at that thing as you can crystallize, and if it wasn't in the right pose, it'd be like something wrong with the crystal. But here it's like, I haven't a clue. I haven't a clue how this thing plays in the pocket. So here you maybe run the Docker, and here's maybe we start going a bit crazy, looking at different structures and maybe different GPCRs that have bound to similar moieties, but they're not aminergic. And with that, I'll get summary conclusion. So hopefully the whole point of this is really how to use pharmacophores to organize SAR data and have a sort of a picture that I can point to and show people, where I found things, where there's some conundrums, etc. And the nice thing is pharmacophore can be used for searching, and we can apply it to VHTS. And it's a substitute, or let's say an alternate to doc. And with that, thank you, and I'll take questions.
Thank you for an awesome talk. Do you have questions? If not, I will start. So what happened to that company?
It was a two-person operation, and wasn't going to work. So actually, the company dissolved, and he's the founder of the company is working for us as an account manager. Yeah. It was a good relationship. He's a great guy. We had good scientific interactions. This was actually, so thank you guys, because this is kind of cathartic. So just a cool little research project that no one's going to get to use or see. But
the potential for future medications for mental disorders, PTSD, things like that. Like it's a shame that the 60s happened and they killed them all.
It's actually quite shocking. There's a paper reviewed in 2012. They kind of bring that up. I've watched these Netflix videos and things like that, and people in psychiatrists like, you're a psychiatrist, you got an MD. You're like, I never heard about this stuff, It was erased, and this review was very much like, no, this wasn't just a fad. There were tens of thousands of papers published in the 50s on this. And what they used to do apparently was that the executives back then, when they were designing new psychotropic drugs, the executives would take them because they would kind of know the effect. It was, well, you've all heard of Timothy Leary, maybe not?
Yeah.
Okay, so Timothy Leary was a disgraced professor in the 60s who. Harvard psychiatry professor who started taking LSD and encouraged everyone to tune in, turn on, drop out. But he said that he learned more from an LSD trip than he did from 20 years of studying psychology, because of the way it opens up your mind. We saw the little plot. Like we're all kind of taking these 4 or 5 little roads home every day, and this kind of just says I'm looking at the whole map, and it does it chemically. So that's the appeal. And the appeal is the neuroplasticity. That's what people. One of the goals is, can we have a rid of the trip? They're studying neuroplasticity now, and for all kinds of headaches and all kinds of different complications. And it makes sense. Like you look at the triptans or the headache medications forever, and there's only slightly different from psychedelics. And psychedelics apparently are maybe doing a better job than the triptans, but the triptans were there because there were psychedelics that didn't make you trip. I don't know. So it's interesting. It's interesting to see the history of all it and how things were influenced, you know, and over time. Yeah. Okay.
So you said that MDMA doesn't act on these receptors, but does this thing where it prevents packaging.
Yes.
So I was curious, like with basically this, the MDMA has an extra methyl group. I mean,
Well, actually, MDMA actually doesn't have the atom in that Q position. When I did the modeling, MDMA doesn't have that atom Q. I need that funny hydroxyl group there. I didn't have all the slides on this, but there's all kind of mescaline analogs, and as soon as you don't have that extra hydroxyl group in that position, you lose the activity. It acts as a VMAT inhibitor, just kind of like disrupts the system of serotonin. That's one of the reasons you can't. It's hard to get addicted to because you take MDMA, it disrupts the packaging, you shoot off all your serotonin, and then you got to wait for your body to build it up again. So even if you take some more the next day, you're already spent, right? So to speak.
You tried some other compounds like methamphetamine or.
Well, there's a great study about that. There was a study that came out that said ecstasy rots your brain. You may have heard that. These scans of rats' brains and things like this was during the war on drugs. Turns out the experimenters weren't using ecstasy, they were using methamphetamine. So the results were completely wrong. It's like, caffeine makes you die, watch. No, you're giving her heroin. So there was the trouble with this field in some ways is that there was a lot of misinformation and disinformation because people will really want to purport this purport how the thing was bad. Like there's theories that LSD have flashbacks, like the LSD molecule hides in your cell for years and then comes back, and it doesn't. A flashback is like a childhood memory because these experiences are very profound. People who get really high on these things, or they say it's one of the 5 or 6 top things that's happened in their lifetime: their wedding, the psychedelic trip, their kids being born, and other things, because it's spiritual. It's a spiritual. That's why I think it works, is because the claim is that people are just awakened in some ways. And the brain scan sort of shows it. There's the ski hill analogy, right? If you ever go skiing, no, think of it as paths, or even better, the way you get home. Right, you get home, the traffic's worse. It's always crap. You're always taking the same road. It's always really ugly. And then finally you say, I'm going to take a different route. And when you take the different route, you realize it's a nice country road, and you say, why am I going that way all the time? And your brain always wants to go that way, but you need to almost chemically stop it. So that's for people who are really depressed, a lot of trauma. They always want to take the bad highway. So that's a way to stop them.
Next question.
Great talk. That was phenomenal. I was wondering, what platform do you use to generate a pharmacophore? Is there anything that, resources online that I can?
Oh, I work for CCG, so I just use the Mo software. Yeah.
There's a bunch of stuff online.
There's a bunch of stuff, and the thing about pharmacophore, it's a very nebulous term. I mean, it's defined by IUPAC, it's the steric and electronic properties. But what do you mean? Like a med chemist thinks of pharmacophores as weighty. I think it was a bunch of spheres in space with volumes. I think OpenEye, it's a shape with some colors, right? So it's pharmacophore is specific, but also very abstract how it was represented. And for a med chemist, the pharmacophore is that 2D cartoon, right? So there's a lot of commonality between what we think is a pharmacophore, but the representations in different softwares can be quite different, right? Because it's not really, it's a human conception, right?
And I would say, it very much resonates. Like, I love working with pharmacophores with med chemists, and especially it's not in CCG, it's in Crescent software, but where chemists hold in their head activity cliffs, it does a really good job of visualizing that. And you had a question.
It was more like how many, and they came in a little bit late, so my apologies. There are companies that are doing research.
Oh, tons of them.
Yeah, so which one is the most advanced in this, and are you working with them?
We're not working with any of them. I was actually one point, there's a company in Australia that they wanted that showed them this research. I'm always just trying to solve. And so I feel like the research was good, right? One about the software. And they didn't want about the software, but they wanted me to be a scientific advisor. This is interesting stuff, But that's a lot of work. But philosophically, I'm thinking, these natural compounds are so profoundly safe. And I think what happened with the cannabis industry, right? So
I don't really.
I personally, maybe they're gonna be ahead, right? But I think this, like with the cannabis stuff, there's gonna be a lot of hype now, right? And a lot of this, like, how are you gonna make money with this? It's kind of so how do you make money? Just one money is develop a brand new psychedelic compound you can pack, new scaffold. That's what I'm talking about here, right? Another way to do it is develop formulations, right? Some of these things aren't orally available, but they have good properties. Maybe if you methylate them or you put it in a little capsule, like a lot of the what was the like Purdue was all formulation, right? They didn't invent oxycontin, they just put it in a pill. So you can, that's another way to go make money. Then the other thing is the actual treatments, like you say, because somebody showed that microdosing doesn't work. It's good for a while, like you don't trip, it's okay, but then actually it kind of doesn't work. So what you really need to do is take a big hit and then don't do it for a couple weeks. So you have to do those kind of blind studies. And we found that, 2 treatments within 2 weeks using this and that, and a lot of the patents are like that. Because what I saw was a ketamine, cannabidiol, and psilocybin as a combined treatment. There's a patent for it. I think that's just a river Saturday night. But that's so. There's other ways. The company's doing all kinds of different things. It's a flurry.
So the actual action is connected with the psychedelic effect.
Well, they're not. See that the jury is out on it. There was a for post trauma and things like that. Some people say, yeah, you need that kick. You need the roller coaster ride, right? Because that's what's going to kick you out. Other people say we can maybe get around that. And for other things like headaches and maybe low level depression, maybe you don't need the ride. Maybe you can have take enough of this where it promotes enough neuroplasticity and neurogenesis that you don't trip, but you overcome some of these mental issues. That's one of the goals, is they want the benefits without the trip. That's like would be one big gold star you want on this.
Thank you.
Welcome. Greg.
Hey, Chris, so on the carbamate, is there any possibility that's negatively charged and you've got a positive charge somewhere?
Might be. I mean that would be interesting. Yeah, that's one of the things where what's interesting about this is the unknown, right? Because the other stuff kind of is known after a while, but so maybe we can talk about it. Is there a positive charge on it? Maybe, I don't know. Could be.
Yeah, I mean, I just wonder if you knew it.
I don't see any basic centers in it.
Well, no, but the pKa on the nitrogen for the carbamate can be low. In theory, it can be deprotonated negative charge.
Ah. But it needs to be positive. It's gonna be counter.
Well, but that's what I'm saying is if you flip your pharmacophore, so the big greasy stuff, you flip your pharmacophore and you have some other positive charge there in the active site.
Oh, okay, maybe it could be a bridge, like you got a negative charge, and it could be a positive charge like calcium or something.
Yeah, so
Or water.
You're ignoring the gas.
Yeah,
Or basically you're chelating with metal.
yeah, that's interesting. That's the thing, like the acid is known, it's the key residue, the span protein, it's like, so something that, although I did find a crystal structure of a transformer that didn't have a charge in it. So, but you're right, maybe some water there, because nature's pretty amazing. You look at these receptors and they look very much the same, but serotonin doesn't hit dopamine, doesn't hit norepinephrine, they kind of tell each other apart, even though they look very much the same, very similar pharmacophores. And I could dock them, each one, the other one fine, and get a good docking score. So nature knows something else, right? And maybe these kind of weird, count ions and waters that we kind of strip out of these models. In some cases, they're playing roles. I'll look into that. That's very cool.
I didn't work a story. I'm gonna date myself. Yvonne Martin back.
What's the sort of that?
I'm gonna date myself a little bit.
Okay, I thought I heard I'm gonna hate myself.
In the late '90s, Yvonne Martin released a data set for MAO inhibitors. And we were all modeling the time. And we all thought we were gods. It was the heyday of pharmacophores, and it turned out that we did have a this is nothing exactly. So that was just a way of just what's old is new again.
Yes.
In the '90s, MAO everyone working, I was like, yeah, we can do anything.
Yeah.
It's a part of it.
Yeah, I mean, I think to us, we've had so few crystal structures back then, right? We had wrote a lot of things. Now it's like almost everything structure based. Like you kind of almost gravitate towards, I got 20 crystal structures, why not use them? This seems kind of rinky dink in some ways, but it has its advantages because you can sort of put just weird hypotheses. Like one thing I didn't show is that we got all these active compounds. If you put a hydroxyl there, all of a sudden you lose activity. Why? Because it looks like norepinephrine. Like there's no interaction, there's no nothing, but serotonin knows it's not serotonin. The H2 receptor knows it's not, and I don't know why, but it's one of the reasons, the only rationale I can have is that when you put that here, nature knows, and I don't have a scoring function, but you can put it there as a blob. Don't have hydroxyl there, which is, but I think that's why I think they do like it, because it's like I can put my knowledge on this. I don't have to sort of look at dials and hope I can press software terms, dial 7.8 or 80, and it becomes almost magic. You know, I don't like,
Yeah.
I don't like a machine where I'm controlling the dials because someone told me how, and I don't really understand how.
It really meshes with the medchem, sort of like you throw up a bunch of designs and go, yeah, that will work, that will work,
Yeah.
that will work. Why did you do that?
Yeah. Yeah, it's cool. It kind of gives you an understanding. I like visual stuff.
Question?
And we do have some food. So what?
If we have no more questions, please join us downstairs at the bar for pizza and drinks.
And more
on-
informal questions.
And more informal questions. Food and drinks on, thank you to see
Yes,
the
yep,
drink.
yep.
BAGIM sponsoring the pizza. Let's go.